High-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion damage mechanisms as a part of uniform or localized loss in thickness phenomena. Description of high-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion based on API 571. The presence of hydrogen in H₂S containing hydrocarbon streams increases the severity of high-temperature sulfide corrosion at temperatures above about 500 degrees Fahrenheit or 260 degrees Celsius. This form of sulfidation usually results in a uniform loss in thickness associated with hot circuits in hydroprocessing units. High-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion refers to the deterioration of metals and alloys exposed to environments containing hydrogen or H2 and hydrogen sulfide or H₂S at elevated temperatures. This form of corrosion can manifest as both general or uniform and localized attack, significantly impacting the integrity and safety of equipment used in industries such as oil and gas, refining, and chemical processing. Here's an overview of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion. At high temperatures, the presence of hydrogen or H2 and hydrogen sulfide or H₂S leads to complex chemical interactions with metal surfaces. These interactions can cause the metal to weaken, crack, or flake away, compromising structural integrity. The corrosion mechanisms are influenced by factors such as temperature, pressure, alloy composition, and the concentration of hydrogen sulfide or H₂S and other impurities. Here's the types of corrosion in high-temperature hydrogen or H2 and hydrogen sulfide or H₂S environments. They are, number 1 is general or uniform corrosion. This occurs when the entire surface of a metal or alloy uniformly reacts with the environment, resulting in a consistent loss of material over the entire exposed surface. In high-temperature hydrogen or H2 and hydrogen sulfide or H₂S environments, uniform corrosion typically involves the formation of protective or semi-protective corrosion products like iron sulfides or other metal sulfides, which can slow down further attack if stable. Types number 2 is localized corrosion. Localized corrosion refers to corrosion that is confined to specific areas, leading to pitting, cracking, or crevice corrosion. This type is more dangerous because it can cause rapid failure with minimal material loss initially. In high-temperature hydrogen or H2 and hydrogen sulfide or H₂S environments, localized corrosion mechanisms include pitting. Small, deep cavities form where the protective film breaks down, often initiated by defects or inclusions in the metal. Stress corrosion cracking or commonly called SCC. Cracks develop under combined stress and corrosive environment, especially in susceptible alloys. Sulfide stress cracking or commonly called SSC, a form of SCC specifically caused by the presence of hydrogen sulfide or H₂S, leading to cracking in susceptible metals. Crevice corrosion occurs in confined spaces where localized chemistry becomes more aggressive due to restricted flow of corrosive agents. Mechanisms of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion includes, the first is, formation of metal sulfides. At elevated temperatures, hydrogen sulfide or H₂S reacts with metal surfaces to form metal sulfides, such as iron sulfide, nickel sulfide. These sulfides can either be protective or non-protective depending on their properties and adherence. The second is, hydrogen embrittlement. Hydrogen atoms generated during corrosion can diffuse into the metal lattice, causing embrittlement and cracking. The third is, reaction with alloying elements. Elements like chromium, nickel, and molybdenum in alloys influence corrosion resistance. The formation of stable, protective sulfide layers depends on their presence. And the fourth is, temperature effects. Higher temperatures increase reaction rates, promote sulfide layer formation, and can lead to the breakdown of protective films. Factors influencing corrosion severity of high temperature of hydrogen or H2 and hydrogen sulfide or H₂S includes temperature. Elevated temperatures accelerate chemical reactions and sulfide formation. Hydrogen sulfide or H₂S concentration. Higher H₂S levels increase the likelihood and severity of sulfide-related corrosion. Metal/alloy composition. Alloys with higher chromium, nickel, or molybdenum content tend to resist corrosion better. Presence of water or moisture. Water can facilitate hydrolysis reactions, affecting sulfide film stability. Stress levels. Mechanical stress enhances the risk of SCC and SSC. flow conditions, turbulent flow can remove protective films and exacerbate localized corrosion. Typical materials susceptible to high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion includes carbon steels, generally less resistant, low-alloy steels, stainless steels, resist better, but susceptible at high temperatures, nickel-based alloys, such as Inconel, Hastelloy, specialized corrosion-resistant alloys. Prevention and mitigation strategies for high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion includes use of corrosion-resistant alloys, applying protective coatings or linings, controlling operating temperatures and hydrogen sulfide or H₂S concentrations, maintaining proper stress levels, regular inspection and monitoring for early detection of localized corrosion. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is a complex process involving chemical reactions that produce metal sulfides and hydrogen-induced damage. It can affect entire surfaces uniformly or concentrate in specific areas, leading to critical failures. Understanding the mechanisms and controlling influencing factors are essential for managing the integrity of equipment operating in such aggressive environments. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion affected materials based on API 571, in order of increasing resistance, carbon steel, low-alloy steels, 400 series SS, and 300 series SS. The materials affected by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion are primarily metals and alloys that are used in environments where hydrogen or H2 and hydrogen sulfide or H₂S are present at elevated temperatures. The susceptibility of these materials to corrosion depends on their composition, microstructure, and protective characteristics. Below is a detailed explanation of the materials affected, categorized by their typical resistance levels and specific vulnerabilities. Common materials affected by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion includes, number 1 is, carbon steel. Composed mainly of iron with minimal alloying elements, the vulnerability of the carbon steel. Highly susceptible to both general and localized corrosion at high temperatures in hydrogen or H2 and hydrogen sulfide or H₂S environments. Corrosion mechanisms commonly affected to the carbon steel, formation of iron sulfides, prone to sulfidation and hydrogen embrittlement. The impact of high-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion to this carbon steel is rapid uniform thinning, pitting, and cracking, especially under stress conditions. The affected materials number 2 is low-alloy steels. Steels with small amounts of alloying elements like chromium, molybdenum, or nickel, the vulnerability of the low-alloy steels. Slightly more resistant than carbon steels but still susceptible to localized attack, especially in high H₂S concentrations, corrosion mechanisms commonly affected to the low-alloy steels, formation of iron sulfides, prone to sulfidation and hydrogen embrittlement. The corrosion behavior of high-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion to this low-alloy steels is formation of sulfide scales that may be protective or non-protective depending on composition and temperature. The affected materials number 3 is stainless steels. Chromium-containing steels, such as 304, 316, designed for corrosion resistance, the vulnerability of the low-alloy steels. Susceptible at high temperatures, especially if the chromium content or alloy microstructure is compromised. The corrosion behavior of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to this stainless steels includes, general corrosion, may occur if protective oxide films are destabilized, localized corrosion, pitting and crevice corrosion are common, especially in environments with high hydrogen sulfide or H₂S and water, sulfide stress cracking or SSC. Cracks can develop under stress due to sulfide-induced embrittlement. The affected materials number 4 is nickel-based alloys. Alloys such as Inconel, Hastelloy, and Monel, containing high levels of nickel, molybdenum, and other elements, the vulnerability of the nickel-based alloys. Generally resistant to H₂S at high temperatures, but not immune. The corrosion behavior of high-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion to this nickel-based alloys is, form stable, protective sulfide layers, however, localized attack can occur if conditions vary or impurities are present. The affected materials. Number 5 is molybdenum alloys and special alloys. High-performance materials with molybdenum additions to improve corrosion resistance, the vulnerability of the molybdenum alloys and special alloys. Better resistance but can still experience localized attack under severe conditions. The corrosion behavior of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to this molybdenum alloys and special alloys is more resistant to pitting and crevice corrosion compared to other alloys. The affected materials. Number 6 is refractory and high-temperature alloys. For examples, tungsten, tantalum, and other superalloys, the vulnerability of the refractory and high-temperature alloys. Typically used in extreme environments, susceptible to sulfidation and hydrogen embrittlement if not properly selected. Material-specific vulnerabilities and affected zones includes, the first is, surface films and scales. Certain materials develop protective oxide or sulfide layers that can be stable or unstable depending on temperature and environment. The second is, localized weak points, inclusions, grain boundaries, and microstructural heterogeneities can act as initiation sites for localized corrosion such as pitting or cracking. The third is, stress concentrations. Materials under mechanical stress are more prone to stress corrosion cracking, especially in susceptible alloys. The choice of materials in high-temperature hydrogen or H2 and hydrogen sulfide or H₂S environments must consider their corrosion resistance, mechanical properties, and operating conditions. Regular inspection, material selection, and protective measures are vital to mitigate damage caused by both general and localized corrosion mechanisms. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion critical factors based on API 571. Number A, the major factors affecting high-temperature sulfidation are the temperature, the presence of hydrogen, the concentration of hydrogen sulfide or H₂S and the alloy composition. Number B, depending on the quantity of hydrogen that is present, corrosion rates may be significantly different than those associated with high-temperature sulfidation in the absence of hydrogen. Number C, sulfidation rates increase with increasing hydrogen sulfide or H₂S content and especially increasing temperature as illustrated in Figure 5.8, corrosion rate of carbon steel in hydrogen or H2 or hydrogen sulfide or H₂S service in a naphtha desulfurizer from the modified Coeur-Gorman curves. Number D, higher corrosion rates are found more in gas oil desulfurizers and hydrocrackers than naphtha desulfurizers by a factor of almost 2. Number E, susceptibility to sulfidation is determined by the chemical composition of the alloy. Number F, increasing chromium content of the alloy improves resistance. See Figure 5.9, corrosion rate curves for various alloys in hydrogen or H2 and hydrogen sulfide or H₂S corrosion service. However, there is little improvement with increasing chromium content until about 7 to 9 of chromium as shown by the relative rate reduction factors in Table 5.1. This table shows the relative corrosion rate reduction factors for different alloys in hydrogen or H2 and hydrogen sulfide or H₂S environments. The baseline is carbon steel with 0.5% MO, which has a rate factor of 1. As we increase chromium content, the corrosion rate decreases, but notice the trend. At 1% of chromium, the improvement is minimal, rate factor only drops to 0.96. At 2.25% of chromium, it's still modest 0.91. Even at 5% of chromium, we're only at 0.80, so the benefit is limited. Significant improvement starts around 7% of chromium or rate factor is 0.74 and continues at 9% of chromium or rate factor is 0.68. This means adding small amounts of chromium doesn't help much in hydrogen or H2 and hydrogen sulfide or H₂S service. You need at least 7 to 9% of chromium for meaningful resistance. That's why alloys like 7 of chromium, 1 of molybdenum and 9 of chromium, 1 of molybdenum are commonly used in high-temperature sulfidation environments. Molybdenum also helps, but chromium is the key driver for sulfidation resistance. Number G, chromium-containing nickel-base alloys are similar to stainless steel. Similar levels of chromium provide similar corrosion resistance. The critical factors of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion are the key environmental, material, and operational parameters that influence the initiation, progression, and severity of both general and localized corrosion in high-temperature environments containing hydrogen or H2 and hydrogen sulfide or H₂S. Understanding these factors is essential for predicting corrosion behavior, selecting appropriate materials, and implementing effective mitigation strategies. Critical factors influencing high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion includes, number 1 is temperature, the temperature impact. Elevated temperatures accelerate chemical reactions, sulfide formation, and diffusion processes. For details, high temperatures typically above 200 degrees Celsius promote the formation of metal sulfide scales, which can be protective or non-protective. Temperatures in the range of 300 to 450 degrees Celsius are particularly critical, as they often mark the transition between protective and destructive sulfide scale formation. Excessively high temperatures can lead to breakdown of protective films, increasing susceptibility to localized attack and embrittlement. Critical factors influencing high-temp hydrogen or H2 and hydrogen sulfide or H₂S corrosion. Number 2 is H₂S concentration. The H₂S concentration impact. The amount of hydrogen sulfide present directly influences the sulfide activity and corrosion severity. For details, higher H₂S partial pressures increase the likelihood of sulfide scale formation, but also promote pitting and stress corrosion cracking. Elevated H₂S levels can lead to the formation of non-protective sulfide layers, exposing underlying metal to further attack. The threshold H₂S concentration defines the critical level above which corrosion mechanisms, especially sulfide stress cracking, are triggered. Critical factors. Number 3 is hydrogen partial pressure and diffusion. The hydrogen partial pressure and diffusion impact. Hydrogen generated during corrosion can diffuse into the metal, causing embrittlement. For details, high partial pressures of H2 facilitate hydrogen absorption into the metal lattice. Hydrogen ingress weakens the metal's ductility and toughness, increasing the risk of cracking and failure. The rate of hydrogen diffusion is temperature dependent and influences the severity of hydrogen embrittlement. Critical factors. Number 4 is material composition and microstructure. The material composition and microstructure impact. Alloy chemistry and microstructural features determine resistance to sulfide formation, hydrogen absorption, and localized attack. For details, chromium, nickel, molybdenum, and other alloying elements enhance resistance by promoting stable, adherent protective layers. Microstructural features such as grain boundaries, inclusions, and defects can serve as initiation sites for localized corrosion. Material susceptibility varies. For example, carbon steels are more vulnerable than high-alloy corrosion-resistant alloys. Critical factors. Number 5 is presence of water and moisture. The presence of water and moisture impact. Water influences sulfide film stability and hydrogen absorption. For details, water can hydrolyze H₂S to produce sulfuric acid or other corrosive species, intensifying attack. Water vapor can facilitate the formation of non-protective sulfide scales. The presence of moisture can also promote crevice and pitting corrosion, especially in confined spaces. Critical factors. Number 6 is stress levels. The stress levels impact. Mechanical stress exacerbates corrosion mechanisms such as stress corrosion cracking, SCC, and sulfide stress cracking, SSC. For details, external stresses or residual stresses in materials can initiate cracks at microstructural flaws or corrosion pits. Stress concentration zones are particularly vulnerable under high H₂S conditions. The combined effect of stress and corrosive environment significantly lowers the threshold for crack initiation and propagation. Critical factors. Number 7 is flow conditions and turbulence. The flow conditions and turbulence impact. Fluid velocity influences corrosion by affecting mass transfer and scale stability. For details, turbulent flow can remove protective films, exposing fresh metal surfaces. Low flow areas, crevices, or stagnant zones favor localized attack, such as crevice or pitting corrosion. High flow rates can also induce erosion corrosion, further aggravating damage. Critical factors. Number 8 is impurities and alloying elements. The impurities and alloying elements impact. Impurities, such as chlorides, oxygen, and alloying elements influence corrosion behavior. For details, chlorides can promote pitting and crevice corrosion, oxygen can destabilize sulfide films and promote oxidation. Certain alloying elements, such as molybdenum, improve resistance, while others may form detrimental phases or inclusions. Critical factors. Number 9 is operational parameters. The operational parameters impact factors like pressure, temperature cycling, and operational duration influence corrosion dynamics. For details, higher pressures increase the partial pressure of hydrogen or H2 and hydrogen sulfide or H2S, intensifying corrosion. Temperature fluctuations can cause thermal stresses and destabilize protective films. Longer operation times allow for the development of thicker corrosive scales or deeper localized attack. Understanding these critical factors allows engineers and operators to optimize conditions, select suitable materials, and implement protective measures to mitigate high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion. Continuous monitoring and control of these parameters are vital for ensuring safety and longevity of equipment in such aggressive environments. High-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion affected units or equipment based on API 571. Number A. This form of corrosion occurs in piping and equipment in units where high-temperature hydrogen or H2 and hydrogen sulfide or H2S streams are found, including all hydroprocessing units such desulfurizers, hydrotreaters, and hydrocracking units. Number B. Noticeable increases in corrosion may be found downstream of hydrogen injection points. The units and equipment affected by high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion are typically components of systems used in oil and gas production, refining, petrochemicals, and power generation where hydrogen and hydrogen sulfide are present at elevated temperatures. These units and equipment are exposed to aggressive environments that can cause both general and localized corrosion, compromising structural integrity, safety, and operational efficiency. Below is a detailed explanation of the key units and equipment commonly affected by high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion. Includes, number 1 is, pipelines and piping systems. Transport fluids, oil, gas, sour water, containing H2S at high temperatures. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion to the pipelines and piping systems, includes, general corrosion, thinning of pipe walls over long distances, localized corrosion, pitting, crevice corrosion, and stress corrosion, cracking at welds, bends, or defective areas, impact, potential leaks, ruptures, or catastrophic failure if corrosion is not controlled. The number 2 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion is heat exchangers. It transport fluids, oil, gas, sour water, containing H2S at high temperatures. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion to the heat exchangers, includes, corrosion of tube materials, especially in the presence of H2S and water, formation of sulfide scales that can spall or cause localized attack, fouling and pitting due to corrosive condensates. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion to the heat exchangers. It reduced heat transfer efficiency, tube leaks, or failures. The number 3 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion is reactor vessels and columns. Process vessels where reactions occur under high temperature and pressure. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion to the reactor vessels and columns, includes, corrosion at welds, interfaces, or microstructural heterogeneities, stress corrosion cracking, SCC, or sulfide stress cracking, SSC, leading to leaks or catastrophic rupture. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion to the reactor vessels and columns, loss of containment, safety hazards, and costly shutdowns. The number 4 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H2S corrosion is valves, fittings, and flanges. Critical control components exposed to process conditions. the vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the valves, fittings, and flanges, includes localized attack at sealing surfaces, threads, and joints, pitting and crevice corrosion under gasket or bolted assemblies, embrittlement and cracking under high-stress and corrosive environment. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the valves, fittings and flanges, leakage, operational failures, and maintenance challenges. The number 5 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is downhole equipment, wells and tubing. Equipment within oil and gas wells, such as tubing, casings, and rods. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the downhole equipment, wells and tubing, includes severe localized corrosion and embrittlement due to H₂S exposure, hydrogen-induced cracking and sulfide stress cracking. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the downhole equipment, wells and tubing, reduced well lifespan. Leaks, or failure of downhole components. The number 6 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is offshore and onshore processing units. Processing facilities handling sour fluids and gases. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the offshore and onshore processing units, includes corrosion of structural steel, platforms, and support structures, pitting and cracking of equipment exposed to sour gas streams. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the offshore and onshore processing units, structural integrity issues, safety risks, and increased maintenance costs. The number 7 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is storage tanks and containment structures. Tanks storing sour liquids, gases, or slurries. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the storage tanks and containment structures, includes corrosion at the tank bottoms, walls, and nozzles, localized pitting leading to leaks or rupture. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the storage tanks and containment structures, environmental hazards, product loss, and safety concerns. The number 8 of the commonly affected units and equipment by high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is valves, pump casings, and compressors. Mechanical equipment with moving parts exposed to corrosive gases. The vulnerability of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the valves, pump casings, and compressors, includes internal corrosion leading to erosion and cracking, hydrogen embrittlement weakening structural integrity. The impact of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion to the valves, pump casings, and compressors, mechanical failure, downtime, and costly repairs. The final remarks from high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion that we can take are included. Localized corrosion typically occurs at welds, joints, and microstructural flaws, leading to pitting and stress concentration points. General corrosion results in uniform material thinning, which can reduce the strength and integrity of entire units. Regular inspection, material selection, corrosion inhibitors, and protective coatings are critical to mitigate hydrogen or H2 and hydrogen sulfide or H₂S induced damage in these units and equipment. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion appearance or morphology of damage based on API 571, number A. Corrosion will appear as a uniform loss in thickness from the process side and is accompanied by the formation of an iron sulfide scale. Number B. Scale is about 5 times the volume of lost metal and may be in multiple layers. Number C. The tightly adherent shiny gray scale attached to the surface may be mistaken for unaffected metal. The appearance or morphology of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion manifests distinctly depending on whether the damage is general or localized. Understanding these morphological features is crucial for diagnosing corrosion types, assessing severity, and implementing mitigation strategies. Below is a detailed explanation of the typical appearances and morphologies associated with high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion. Includes, number 1 is general or uniform corrosion morphology. The appearance of general or uniform corrosion includes uniform thinning. The metal surface exhibits a relatively uniform reduction in thickness without pronounced localized features. Surface roughness. The surface becomes rougher and may appear dull or matte due to scale formation and metal loss. Color changes. Depending on the process environment, surfaces may display discoloration, such as bluish, brownish, or blackish hues, due to oxide or sulfide scale formation. The morphological features of general or uniform corrosion includes oxide or sulfide scales, includes thin, adherent, and continuous films of metal oxides or sulfides. The scales are often layered, with inner layers being more adherent. Scale characteristics: protective versus non-protective. In some cases, scales are dense, adherent, and protective, reducing further corrosion. In other cases, scales are porous, flaky, or brittle, promoting continued attack. Surface topography includes generally smooth to mildly rough surfaces, minimal microstructural features or pits. The microscopic features of general or uniform corrosion includes uniform corrosion zones with no significant microstructural attack. Presence of microcracks may occur if thermal stresses develop but are usually minor. The number 2 of the appearance and morphology of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is localized corrosion morphology. Localized corrosion involves specific sites where corrosion is intensified, leading to features such as pitting, cracking, or crevice attack. The appearance and features of localized corrosion: number A, pitting and puncture holes, small cavities or pits, deep, narrow, and well-defined cavities or holes on the surface. Size distribution: pits can vary from microscopic to several millimeters in diameter, often dispersed randomly. The morphology of pitting and puncture holes: spherical or irregular pits, sharp, often steep-sided profiles. Pits may be several micrometers to millimeters deep. The surface around pits may appear relatively smooth or slightly corroded. The scale and composition of pitting and puncture holes: inner surfaces of pits may contain sulfide deposits, corrosion products, or porous scales. Pits are often filled with dark, sulfide-rich deposits. The number B of the appearance and features of localized corrosion is crevice and gap corrosion. The appearance could occur when attack within crevices such as gasket interfaces, welds, or bolt holes. The morphology of crevice and gap corrosion: narrow, elongated corrosion zones, often filled with corrosion products or moisture. Features include undercutting of the metal at the crevice edge. The number C of the appearance and features of localized corrosion is stress corrosion cracks, SCC, and hydrogen-induced cracks. Transgranular or intergranular cracks that propagate under stress. The morphology of stress corrosion cracks, SCC, and hydrogen-induced cracks: fine, branched cracks often aligned with microstructural features. Cracks may be filled with corrosion products. Fracture surfaces may show brittle characteristics. The number D of the appearance and features of localized corrosion is sulfide scale and deposit features. Non-uniform, porous, or spalled sulfide scales. The morphology of sulfide scale and deposit features: areas of scale spallation exposing fresh metal, layered or flaky deposits, presence of black or dark sulfide deposits on the surface. The microstructural features of the localized corrosion morphology: localized attack often initiates at microstructural heterogeneities, grain boundaries, inclusions, or microvoids. Pitting is often associated with microgalvanic cells between different phases or impurity sites. The number 3 of the appearance and morphology of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion is scale and deposit morphology. Includes: the first is protective scales, dense, adherent, and uniform sulfide or oxide layers, may appear as shiny, dark, or matte films depending on composition, and the second is non-protective scales, porous, flaky, or loosely adhering deposits. Often spall off under thermal or mechanical stresses. In summary of the appearance and morphology of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion, general corrosion manifests as a uniform, dull, and relatively smooth surface with a consistent oxide or sulfide scale. Localized corrosion presents as discrete pits, cracks, or crevice zones, often with dark sulfide deposits, sharp edges, and microstructural features indicating microgalvanic attack or stress-related cracking. The scale morphology varies from dense and protective to porous and spalling, heavily influencing the corrosion process. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion prevention and mitigation based on API 571. Number A, the corrosion damage is minimized by using alloys with high chromium content. Number B, the 300 series SS such as types 304L, 316L, 321 and 347 are highly resistant at service temperatures. Preventing and mitigating high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion, whether general or localized, is a critical aspect of maintaining the integrity, safety, and longevity of equipment and units exposed to sour, high-temperature environments. The strategies involve a combination of material selection, operational controls, chemical treatments, protective coatings, and regular inspection. Below is a detailed explanation of prevention and mitigation methods for high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion. Includes, number 1 is material selection and design, includes, number A, use corrosion-resistant materials, includes, the first is alloy selection, use of corrosion-resistant alloys such as stainless steels, e.g., 316L, 904L, duplex stainless steels, or nickel-based alloys, Inconel, Hastelloy, materials with high chromium, molybdenum, or nickel content offer better resistance to sulfidation and high-temperature oxidation. The second is microstructure optimization, avoid microstructural heterogeneities that promote localized attack, such as inclusions or grain boundary precipitates. The third is design considerations, minimize crevices, sharp corners, and weld defects that can promote localized corrosion. Proper flow design to prevent stagnant zones. Number B of the material selection and design is use of protective coatings. Applying high-temperature resistant coatings such as ceramic coatings, metallic overlays, or paint systems designed for sour environments to protect the substrate. Number 2 of prevention and mitigation methods is operational controls, includes, number A, control of process chemistry, includes, the first is hydrogen sulfide or H₂S management, keep hydrogen sulfide or H₂S partial pressures at the lowest feasible levels, avoid conditions that favor high hydrogen sulfide or H₂S concentrations. The second is temperature control, operate below critical temperature thresholds where sulfide scales become porous or non-protective, use process control to avoid thermal excursions that can damage protective scales. Operational controls. Number B is, control of water content, minimize free water in high-temperature environments since water facilitates sulfide scale formation and corrosion processes. Operational controls. Number C is, pressure and flow management, maintain adequate flow velocity to avoid stagnant zones and reduce localized attack, avoid pressure drops that can cause condensation and crevice formation. Number 3 of prevention and mitigation methods is corrosion inhibitors and chemical treatments, includes, number A, inhibitors, use of corrosion inhibitors, such as amines, thiol-based compounds, that form protective films on metal surfaces. Inhibitors are particularly effective in controlling general corrosion but may have limited impact on localized attack. Number B, scales and deposits control. Chemical treatments to promote formation of protective sulfide scales that act as barriers. Use of scavengers to remove free H₂S or water-soluble sulfides. Number 4 of prevention and mitigation methods is design and maintenance strategies, includes, number A, regular inspection and monitoring, use non-destructive testing, NDT, methods such as ultrasonic testing, radiography, or visual inspection to detect early signs of corrosion, monitor corrosion coupons or probes to assess corrosion rates. Number B, cleaning and repair. Periodic cleaning to remove corrosive deposits or scales, repair or replace damaged equipment promptly. Number C, cathodic protection. Employ cathodic protection systems, such as impressed current or sacrificial anodes, to reduce electrochemical corrosion, especially in structural steel. Number 5 of prevention and mitigation methods is localized corrosion prevention, includes, number A, avoid microstructural heterogeneities, use high-quality, weld-free, or properly welded joints, post-weld heat treatments to reduce residual stresses and microstructural defects. Number B, design against crevices and stagnant zones, proper gasket and joint design. Eliminate crevice-forming geometries or use corrosion-resistant materials in crevice zones. Localized corrosion prevention and mitigation. Number C, stress management. Minimize residual and operational stresses to reduce susceptibility to stress corrosion cracking. Number D, use of sacrificial or corrosion-resistant linings. Linings or sleeves made of corrosion-resistant materials in critical localized zones. Prevention and mitigation of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion involve a comprehensive, multi-layered approach, includes selecting appropriate materials and designing equipment to minimize corrosion risk, managing process chemistry and operational parameters to inhibit corrosive reactions, applying protective coatings, chemical inhibitors, and cathodic protection. Implementing rigorous inspection, maintenance, and repair programs to detect early signs of corrosion and prevent catastrophic failures. High-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion inspection and monitoring based on API 571, number A, UT, VT and RT thickness readings are used to monitor loss in thickness. Number B, actual operating temperatures should be verified in the field to compare against design. Number C, process simulations should be checked periodically to confirm that H₂S levels have not significantly increased. Inspection and monitoring are vital for detecting, assessing, and preventing high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion, both general and localized. Effective strategies involve a combination of non-destructive testing, NDT, chemical analysis, and real-time monitoring techniques. Below is a detailed overview of the most commonly used inspection and monitoring methods for detecting high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion. Number 1 is visual inspection. This is purposed to detect surface degradation, corrosion products, cracks, pitting, spalling, or deposits. The method of visual inspection are including regularly scheduled inspections using borescopes, magnifying lenses, or remote cameras. Visual signs include discoloration, scale formation, blistering, cracking, pits or corrosion deposits. The limitations of visual inspection are including, cannot quantify corrosion rate, surface only, deeper damage may be missed. Inspection and monitoring methods. Number 2 is ultrasonic testing or UT. This is purposed to measure wall thickness reduction due to corrosion, and also purposed to detect internal flaws, cracks, or laminar corrosion. The method of ultrasonic testing or UT are including, use of ultrasonic transducers to send high-frequency sound waves into the material. Thickness gauging involves measuring the time it takes for echoes to return. Phased array ultrasonic testing, PUT, enhances defect characterization. The application of ultrasonic testing or UT are including, suitable for both general thinning and localized corrosion, pitting or cracks. Periodic thickness measurements help quantify corrosion rates. The advantages of ultrasonic testing or UT are including, non-contact or contact methods, can inspect through coatings or insulation with proper techniques. Inspection and monitoring methods. Number 3 is radiographic testing or RT. This is purposed to detect internal corrosion, cracks, or voids. The method of radiographic testing or RT are including, X-ray or gamma-ray imaging to visualize internal features, used mainly for weld inspection and internal corrosion detection. The limitations of radiographic testing or RT are including, less effective for surface corrosion, requires access and safety precautions. Inspection and monitoring methods. Number 4 is magnetic particle testing or MPT and dye penetrant testing or DPT. This is purposed to detect surface cracks or flaws in ferromagnetic materials. The method of MPT and DPT are including, MPT apply magnetic field and magnetic particles to surface, irregularities attract particles. DPT apply dye penetrant to surface, defects trap dye, visible under UV or normal light. The limitations of MPT and DPT are including, surface only, less effective at high temperatures. Inspection and monitoring methods. Number 5 is electrochemical and corrosion monitoring techniques, includes, number A is using corrosion coupons. This is purpose to measure corrosion rates over a period. The method of using corrosion coupons is to deploy metal coupons, small samples, in the process environment, retrieve periodically to measure weight loss or surface changes. The application of using corrosion coupons is quantitative assessment of general corrosion rate. Number B is using electrical resistance or ER probes. This is purpose to continuous corrosion rate monitoring. The method of using electrical resistance or ER probes is thin wire or foil exposed to environment. Resistance change correlates with metal loss. The application of using electrical resistance or ER probes is real-time, long-term monitoring. Number C is using linear polarization resistance or LPR probes. This is purpose to rapid estimation of corrosion rate. The method of using LPR probes is small potential perturbations applied, measure current response. The application of using LPR probes is for corrosion management systems. Number D is using electrochemical noise monitoring. This is purpose to detect localized corrosion activity. The method of using electrochemical noise monitoring is to measure spontaneous fluctuations in potential and current. The application of using electrochemical noise monitoring is for identification of pitting or crack initiation. Inspection and monitoring methods. Number 6 is advanced and specialized techniques, includes, number A is using acoustic emission monitoring. This is purpose to detect active cracking or pitting events. The method of using acoustic emission monitoring is to sensors pick up high-frequency stress waves emitted by crack growth. The application of using acoustic emission monitoring is for early warning of localized damage. Number B is using fiber optic sensors. This is purpose to provide real-time temperature, strain, or corrosion signals. The method of using fiber optic sensors. Embedded sensors in materials for continuous data. Number C is using surface analysis techniques or post-inspection, scanning electron microscopy or SEM. Examine corrosion features at micro/nano scale, energy dispersive X-ray spectroscopy or EDS, analyze corrosion deposits composition, X-ray photoelectron spectroscopy or XPS, surface chemistry analysis. Inspection and monitoring methods. Number 7 is monitoring of corrosion products and deposits, includes, number A is sampling and chemical analysis, collect corrosion deposits or scales, analyze for sulfide content, pH, or other corrosive species. Number B is deposits inspection, use endoscopes or borescopes for internal surfaces. Inspection and monitoring methods. Number 8 is operational and process monitoring, includes, number A is process data, monitor parameters like temperature, pressure, H₂S partial pressure, and flow rates, used to correlate corrosion activity with operational conditions. Number B is environmental sensors, measure H₂S concentration, water activity, or dew point. Effective detection and monitoring of high-temperature hydrogen or H2 and hydrogen sulfide or H₂S corrosion require a multi-method approach tailored to the specific environment, equipment, and corrosion types. Regular visual inspections combined with quantitative measurements like ultrasonic thickness and electrochemical probes ensure early detection of both general and localized corrosion, enabling timely maintenance and mitigation actions. Thank you.